So we are working on applications of the derivative. In the last video, we introduced how it applies to money. We did a specific example over expenditure, but I also explained the profit equation to you. So, to review, profit is revenue minus cost. And this is what we are going to be using in this example. Example here is a manufacturer can produce digital recorders at a cost of $50 a piece, so $50 per unit. It is estimated that if the recorders are sold for P dollars a piece, consumers will buy Q equals 120 minus P recorders a month. So we have four parts to this. First, we want to come up with the profit equation as a function of P, and where P is the amount that they are sold for. Second part, we want to come up with the manufacturer's profit as a function of Q, and Q is the amount that the consumers are going to buy. Then we want to figure out the average rate of change in profit as the level of production increases. And last but not least, not the average rate, but the actual rate of the profit at a specific time. And of course, isn't increasing or decreasing at that time. So let us go ahead and start with part A. Express the manufacturer's profit as a function of P. Well, we're going to start with our generic profit equation. So capital P stands for profit. Now I'm just going to label it as X here, but eventually I'm going to substitute my P in. Profit is my revenue minus my cost equation. Okay. Now remember, if we had it per unit, then we need to apply that as well. So we do have that here. They give us a specific number of units, so we have to apply that or multiply that times the number of units, which in my generic equation stands for X. We'll have to figure out what that is in this specific equation. Okay, that's my generic equation as a function of X. We want to come up with my profit equation as a function of P here. So first I need to figure out what my revenue is, the amount of money that we're bringing in, and that's specifically P dollars a piece, okay, minus the cost, how much it's costing us to make these, and that was a flat rate of $50 a piece, times the number of units. Well, the number of units is defined as Q here. Or if I substituted that in as a variable of P, that would be 120 minus P. So my profit as a function of P, meaning how much they are selling for, would be this equation here. Now, if there was a need for it, you could simplify this equation by FOILing it out. So I went ahead and worked it out over here, and so that gives me my final answer. Profit as a function of P, or the amount that we're selling them for, is negative P squared plus 170P minus 6,000. Okay, we're going to keep this in mind because that's going to help us with part B. We don't want profit as a function of P. We actually want profit as a function of Q, meaning how many are consumers actually buying, or in the case of how many are we actually selling at that time. So let me start by setting it up the same way that I had it before. Profit as a function of P was defined as my revenue, which was lowercase p, minus my cost of 50 times the number of units. Well, our number of units was defined as Q. So at this point, it was half as a function of my variable P and half as a function of my variable Q. In part A, we went ahead and we substitute in what Q was here. And that was an easy substitution to give me a function of my lowercase p. Here, instead of me substituting in Q to replace it with P, what I'm going to do then is I'm going to have to figure out something for P to replace it with Q. So remember, I want this as a profit equation as a function of Q. So I need to replace P with something here in terms of Q. Well, what we do then is we take this formula and we adapt it. If Q equals 120 minus P, what we can do is we can solve for P. So basically, Let me rearrange where Q and P are by adding P to both sides to canceling it out, but subtracting Q from both sides to canceling it out. So that gives me the formula that P is equal to 120 minus Q. So instead of making the substitution exactly like I see it, I just have to finagle it a little bit to make the substitution like the problem actually wants it. So instead of me substituting in the Q, I'm substituting in this P here. So that gives me 120 minus Q. So simplifying this, my 120 minus 50 gives me a 70 minus Q. And if I multiply that by Q, that gives me 70Q minus Q squared. Or if you like to put it in descending order, that would give me negative Q squared plus 70Q. And so there we have our profit function of Q, meaning all of the variables in my equation are Q variables. Okay. The reason that we want it as a function of Q, meaning how many consumers will actually buy or how many we are wanting to sell, that's going to help us analyze it in the next two parts of this equation. So there we wanted the average rate of change in part C and the actual rate of change in part D. So we know that our profit equation as a function of Q is equal to what we just came up with, negative Q squared plus 70Q. And we wanted it as a function of Q because notice what they have in our parts B and C. They give us the variables when Q is equal to 0 and Q is equal to 20. That's why we need this as a function of Q. Same thing in part D, they do it when Q is equal to 20. So we need to make sure that our variables are consistent. So even though it might have been easier in part A to figure out my profit function as a function of P, meaning the amount that we sold them for, it actually makes more sense to utilize it as a function of Q. How many products are we actually selling at this point? Okay, I am not going to work these out for you step by step because I've already shown you lots of examples of this in other videos. So I'm going to just give you the answers to confirm that you can compute these correctly on your own. So here's the time to pause that video. Okay, here's the answer to part C, where we wanted the average rate of change. You use the slope formula. To compute your two y values, you plug your two x values into your equation, our profit equation that we found in part B, and that gives us our values here. Simplify them, and that gives us 50. Remember, when you want to label rate, you have something per something. In this problem, we have dollars per recorder. So our final answer is $50 per recorder. Okay, now on to part D. Okay, so I worked out the answer to part D. I have found my derivative, and there is my definition there. I have substituted in the Q plus H. I canceled out with my original function, eliminated my H's, substituted in my 0 for the limit, and so I get my derivative, or the P prime of Q, is negative 2x plus 70. Then, when we want what is the rate of the profit when Q equals 20, that means we substitute 20 into our derivative notation. We come out with 30, and we know that our rate here is dollars per recorder. So we can do the math, and we can probably even get the label here. But again, what does this really mean? So this means, okay, remember Q is the number of recorders each month that people are buying. So if people are buying 20 recorders per month, then the rate that we're selling them at is $30 per recorder. Now, if the consumers were buying more or less recorders per month, then that affects the rate that we can sell these recorders at. If the consumers are buying more, that means we can raise the price. If consumers are buying less, that means we need to lower the price. We need to keep everything at an equilibrium. But at this rate, when consumers are buying 20 recorders each month, the rate that we're selling them for is $30 per recorder. So this finishes up my profit examples, and in fact, this actually finishes up all examples of applications of the derivative. So now not only can you compute the derivative, you should be able to apply it in almost any different type of problem that you can see out there.